Welcome back to ECE 501B. I'm not sure how anxiously you're watching the D2L website to see if there's a homework assignment or when it's posted. There is one. The due date is a little different than in the past. This one needs to get us up through some more of Chapter 3 material, and so I've delayed when it is due. The first exam is basically a week and another period beyond that. So we'll probably have another homework assignment prior to exam number 1, which will be homework 4. It'll be a week after that. That's the plan right now. What I want to do today is get more into chapter 3, which is linear maps. That's taking this function, essentially, t, and mapping points between two different vector spaces, a vector space V and a vector space W. They don't have to be the same vector space. We briefly were talking about the null space last time. We'll hopefully review a little of that. We'll go over the definition and remind ourselves that, well, we actually will maybe show this. I can't remember now where we've been and where we're going. But we'll show that the null space is a subspace, and it's a subspace of the domain vector space V. That's where our vectors are coming from before we map them into where they're going, and they're going into what I might call the codomain. We'll see there's a strong connection between null space and what's called an injective map. And if you're having trouble injective, surjective, maybe keep in mind of some of the letters that are in these different words. Injective has an N in it, and it's related to or connected with the null space. Null is N. And hopefully you're starting to get comfortable with the null space. We'll become a little bit more comfortable with the range space. And these maps called surjective maps, they are connected with the range space. We'll look at the properties of these injective and surjective maps and what that means relative to the dimensions of the domain and the codomain. And then we will maybe go to a more practical application and move a little bit away from the abstractness of these concepts and represent these linear maps with matrices. How do they come into a matrix representation? And once we have this matrix representation, then we'll start talking about maps being invertible, isomorphic spaces, etc. But that's where we're headed. Let's, as a review, remind ourselves of where we have been, and that was with this concept of a null space, and these blobs that are on the paper are representing the two different vector spaces, V for the domain and W for the codomain. The null space of T, if it's non-empty or if it's non-trivial, it's going to be a set of vectors in our domain. So there will be vectors in V that when they get mapped through this linear transformation go actually to the zero vector in our codomain W. Meaning we could have a vector X get mapped over here to 0. We could have a vector Y in this space, and it also goes to 0. Those vectors are then in this null space of this mapping V. In set notation, we could say, and I may use this script N and a script R to represent range, N for null space. I may write it out. I think the book writes it out. But the null space is this set of vectors in the domain, set V. Here's our domain, such that those vectors, when mapped through the linear transformation T, end up going into the 0 vector in our codomain. And now we are sort of maybe trying to be a little bit more subtle with codomain versus range, because the range space may not cover all of the codomain. So I'm trying to make this distinction. I may get sloppy and say, oh, the range of that mapping. Well, the range of that mapping may be a subspace of the entire codomain. That's why I'm trying to maybe make this distinction. So here are some examples, and I think we talked about this first one last time, and that's why I'm just going to quickly scroll through it. The differentiation map, where this is a linear map that transforms or that maps this set of polynomials into the set of polynomials. The null space of such a map really only consists of these polynomials that are constant. So if I gave you p of x equal to 3, then when you take the derivative of that with respect to x, it's going to get mapped to 0. I give you 10, p of x or q of x equal to 10. Now I take the derivative of q of x, the result is 0. Meaning the set of all real numbers that are constant belong to the null space of T, where T is this linear map that's the differentiation operator. So it's this operation of differentiation. And the null space of that operation consists of all vectors, in this case, that are simply constant. They don't have any x terms, they don't have any x squared terms, no x cubes, they don't have any x's in them. They're only constant. That then would be our null space of this linear map, T. Another example of where this null space might happen is if we were doing a linear transformation or a linear map from one vector space, in this case, three-dimensional space, R3, down into a two-dimensional space. And let's just say that that mapping is defined by this relationship between the three coordinates x, y, and z in R3 into, let's say, coordinate 1 and coordinate 2 in this two-dimensional space, R2. This now changes the dimension. It's a linear map, and what does it require for a map to be linear? As a sort of a reminder, we need it to satisfy a couple of things. It needs to additivity and homogeneity, or this scalar multiplication property. Those two properties allow these maps to be linear. In this case, this is a linear map that's actually changing the dimension. It's going from an R3, three-dimensional space, down to something that's consistent with a plane. And now what we want to do, we want to find, are there non-trivial vectors in this three-dimensional space, x with coordinates x, y, and z, that will actually map into the 0 vector in this two-dimensional space. That means really that we're looking to see simultaneously, can we find x, y, and z that satisfy 2x minus y plus 3z, and at the same time 7x plus 5y minus 6z equal to 0. If we can find combinations of x, y, and z that satisfy these two relationships, then those values of x, y, and z would actually be in the null space of this linear operator T. Is that clear? And now we're looking to see, are there combinations of x, y, and z such that that is true? Or we could write it the null space of T, or this script of T is this three-dimensional vector. So x, y, z is an element of R3 such that these two relationships hold. And those are just the ways that the first coordinate and the second coordinate are defined in this new two-dimensional space. And if you set up the equations, you can find that the null space of T actually is along a line in this three-dimensional space. If X, Y, and Z are in the proportions given by this sort of not real neat relationship, then points on that line will map to 0, 0 in the two-dimensional plane, or this two-dimensional space. Questions on that? And there we were going from 3 to 2, weren't we? A dimensional 3 to a dimensional 2. And that's more typical in terms of where you think you are going to have a non-trivial null space, is when you go from a higher dimension to a lower dimension. But you could also, depending on the given relationships, you could also have a non-trivial null space, meaning something other than the 0 vector mapping to the 0 vector. You could have that if you were going from a smaller vector space to a larger vector space. For example, suppose that we have a linear map T from R3 up to R5, where now this linear map is going to map this 3 vector into a 5 vector, where the first component of that 5 vector is related to those 3 coordinates of the vectors in the domain is minus x plus y minus 3z. The second coordinate is minus x plus 2y minus 4z. The third coordinate is x plus y plus z. The fourth coordinate is 2x plus 3y plus z. And the last coordinate is x plus 2z. In order for T to have a non-trivial null space, something other than the 0 vector, something other than x equals 0, y equals 0, and z equals 0, then we need all 5 of these equations to simultaneously equal 0. We need to find values for x, y, and z that simultaneously satisfy those formulas or those expressions equal to 0. So for the null space, we actually need, I'm going to get kind of concise, we need the right-hand side, that's those relationships there, to equal this 0 vector in R5. You can show that doing that actually does produce a non-trivial relationship between the x, the y, and the z, even though we're going from a smaller dimensional vector space to a larger dimensional vector space. You can show that the null space of T is in the span, or is spanned by, -2, 1, 1. And if you plug in x equal -2, y equals 1, and z equals 1, you will see that each of these 5 relationships goes away, or vanishes, or becomes equal to 0. And the interesting part about this example is that the dimension of our domain, where here was our domain was this 3-dimensional real vector space, that was equal to 3, and that was actually equal to, or I'm sorry, less than the dimension of our codomain, which was equal to 5, and yet we still had a non-trivial null space. It just depends on the relationship between these different vector spaces, whether or not you have a non-trivial null space. Now, let's show or convince ourselves that that null space that we've now created or looked at in a few ways actually forms a subspace. So the null space, we've been sort of assuming that or saying that, the null space of a linear map, or maybe we just assumed it, T, such that we map V into W, is a subspace. And where is it a subspace of? It's of the domain, isn't it? It's a subspace within the domain, V, vector space. Now, if we wanted to show this or prove that something is a subspace, what do we need to show? You remember how many properties it needs to possess? It's this magic number 3, isn't it? So the subspace must satisfy 3 properties. One of those 3 properties is this subspace needs to contain the additive identity. Let's see if indeed it does. Well, we know that the additive identity in V is 0. But inside that argument, we could actually add the additive identity. The vector space V has an additive identity, so now we're actually using that fact. We're looking at the additive identity in V. But now we can use this linearity property of the linear map, T, and say T of x plus y, where in this case x is 0 and y is 0, is the same as T of x, which is 0, plus T of y, which is also 0. So this is now the additivity of the linear map. But now what do we have? Now that's actually 2 of T of 0. So we now have something equal to twice its something. And when is that going to happen? When that something is 0, or the 0 vector. And that's what we wanted to show, that T of the 0 vector is indeed equal to the 0 vector. And this 0 vector is in the codomain W. So now we know the null space of T contains the additive identity. And this one is actually in V. It satisfies the first property. Now we want it to be the null space. We need it to be closed under addition. For the second property. In that case, what we want to simply do is just take a couple of vectors belonging to the null space of T and see if their sum belongs to the null space. meaning now we have t of u plus v, but we know that this linear map has linearity properties, so that's the same as t of u plus t of v. But u and v were assumed to be in the null space, so t of u is 0, t of v is 0, and that says that 0 plus 0 is 0, which is an element in W, but u plus v were in the domain, but now that combination is also in the null space of T, and so it is closed. Since u and v were arbitrary vectors in the null space of T, then we've now concluded that the null space of T is closed under addition. Now finally, we need to see if it's closed, this subset, to see if it's a subspace. It needs to be closed under scalar multiplication. Now we take a vector in the null space of T, let's call that u, and we take a scalar that's in our field of numbers, which let's say is an element of F. Now we look at T of AU, but we know the linearity property of this linear map allows us to say that's A of TU, but TU, since U is in the null space of T by definition, is 0, and any scalar times the 0 vector gives us back the 0 vector, and that now allows us to say that AU is in the null space of T. And now we've shown all three properties are true, and now we can say that the null space of T is a subspace of our domain space V. And that's a nice thing to have. Now any vectors in the null space of T, they form a subspace, and now we can play with that as if it's a subspace, and that gives us all these nice properties. Let's now talk about this notion or term that's related to the null space, but it's now this term injective. Here's our definition of what we mean by a map being injective. First, let's start with the fact that we have a linear map that is mapping between two vector spaces V and W. That's given. Now, if whenever we have two vectors, U and V, that are in the domain, and T of U equals T of V, implies that U must equal V, then the map is said to be injective. Or you might hear some books or people call this a one-to-one mapping. So that's what we mean by a map being injective. And what we want to remind ourselves of is that we already, with this linear map, T of U gave rise to a unique vector in W, in the codomain. So T of U was already selected, or T of U already, maybe I should say T of U already selected a unique element in W. So when we pick a U in our domain, then that's going to give us a unique value in our codomain, which we were calling maybe W, little w. So now what we can conclude from that is in an injective map, only a single element of V maps to that unique element W in W, maps to that unique element in W. And there's where this one-to-one correspondence comes into play. Or maybe let me just say a one-to-one relationship between the elements of V and W. A sort of basic picture of that might be the following. Maybe we have some points in V that are getting mapped into W through this linear transformation T. This transformation T takes us from an element in V into a unique element, and there's really only one element in V that corresponds to producing this element in the codomain W. Now there could be extra locations in the codomain that don't get touched by this map of T from V into W, but this now shows that we do have a one-to-one connection with this function or this map T. Another way of looking at that in terms of, let's say, V and W are both just one-dimensional, or the real line, an injective map could be thought of in the following way. We could say, here is a mapping, an f of x from an x. Let's say our x is now this V, and the y coordinate is our W. Then an injective map would be something like that, where if this is now x is an element of V, and now f of x is an element of W, this is now our f of x. And if we thought about a horizontal line, if that's very horizontal, But if that was a horizontal line, that only intersects this function in one location. So this is a simplistic picture or image of an injective map, but each horizontal line only passes through one point on f of x. And that's what we mean by injective. We take an element in our domain, and that maps into an element in the codomain, and that, if we end up at the same spot in the codomain, that means that we actually started from the same location in the domain set. If we end up in a different spot, then we had to start from a different location. The values in the domain were not equal if we end up in two different locations in our codomain. Now that actually allows us to find a pretty strong relationship between this injective map and the null space. So there's a strong relationship, and that's what I meant by injective having the N and null space. There's a strong relationship between the null space of a map and whether that map is injective. And that's actually in the textbook, Proposition 3.2. Proposition 3.2 says if we have a linear map between V and W, that map is injective if and only if, that's what I mean by IFF, if you were wondering where that English word came from, but if and only if is abbreviated IFF, if and only if, the null space of T is the zero vector. If T is injective, then the only element in the null space of T is the zero vector. We have a unique vector that maps to the zero vector in the codomain. And that's what we said an injective map had to be. We can't be coming from three different locations in the domain and ending up at the zero vector. Then it wouldn't be injective. Now, in order to prove that or to show that, if this is an if and only if proof, what do we do with if and only if proof? So again, we're sort of going back and reminding ourselves or learning some of these proof techniques. If we have an if and only if proof, that usually means we have to prove it twice in both directions. So here, let me just say to prove an if and only if we have to show implication in both directions. So first, let's just assume that we have an injective map. So now assume T is injective. And we need to show then that that implies that the null space of T is only the zero vector. That's what we're hoping to show, or that's the concluding statement that we're trying to show is true. So let's assume T is injective. Let's take a V that's in the null space of T. That means that TV, not television, but TV, if you're following along with the English version of this show. So T operating on this vector V, and this vector V belongs to the null space of T, that gives us 0. And that's because V is in the null space of T. Now, we also need to remember what was the null space of T. What was one of the nice things about the null space of T? It was a subspace, wasn't it? And if it's a subspace, what does a subspace have to contain? It has to contain the zero vector or the additive identity. So now remember from the previous proof, we now know that 0 is in the null space of T. So that says then that we have this T times 0 is equal to 0. Where this is now the zero vector in the domain. And the result is the zero vector in W. Well, now we have TV equals 0 and T0 equaling 0. And those then, what did we assume? That our map was injective. So that implies that the arguments have to be the same if their result of the map is equal to each other. So now this says, since TV is equal to 0 is equal to T of 0, by definition of a map being injective, that implies that the arguments of that operation must be the same. Now we have our implication in one direction. We assumed our map was injective, and we just used it in this last step. That implies that the null space of T is equal to 0. Meaning, given any vector V that's in the null space of 0, I'm sorry, in the null space of T, it has to equal 0 if our map is injective. Now let's go the other direction. The next direction of implication is, let's assume that the null space of T is the 0 vector. Now let's take a couple of vectors. So now let's take U and V, both in V, in the domain. And let's assume that TU is equal to TV. So let's assume that they map to the same location in our codomain. Then 0, by the additivity of our linear operator, can be formed by tu minus tv if tu equals tv. But this now, again using the linearity property of our operator, says that that's equal to t operating on u minus v. Well, now if we sort of look at what we've just derived, now we have t of u minus v actually equaling the 0 vector. But what does that mean about t? I'm sorry, what does that mean about u minus v? Or I'm getting ahead of myself. I gave you the answer, didn't I? U minus v lives in the null space of t if operating on it with t maps you to the 0 vector. So u minus v is in the null space of t. Well, if u minus v is in the null space of t, we assume that the null space of z was the 0 vector. So now we know that u minus v is the 0 vector, or u is equal to v, which says that when tu is equal to tv, that implies u is equal to v, and that's the definition of a map being injective. And that's the other implication, which means if the null space of t is only the 0 vector, then that implies that t is an injective map. So now we've proven it both ways, and that then says that we can say our map is injective if and only if, or maybe we could say t is injective if and only if the null space of t only includes the origin. Questions on that? So now we have this sort of way of checking to find out if a map is injective. If we can find the null space of that map, then we're looking to see, is that null space trivial? Does it only contain the 0 vector? If it's non-trivial, then we know that map is non-injective. Here's sort of a picture of what we have, of a non-injective map. And I think you can already probably sketch it. We have now something here, and we might have some points in our domain getting mapped into our codomain via t. And now maybe this is our point in W, and maybe all three of these go to the same point. And if you have a non-trivial null space, it's pretty easy to come up with an infinite number of vectors in your domain that will map into various locations in your codomain, because you can just add in to your original vector something in the null space, a vector in the null space. So here are some things to keep in mind. First, n of t is non-trivial. Is it clear what I mean by the null space of t being non-trivial? It's something other than the zero vector. So the null space of t is non-trivial for a non-injective map. And if you wanted to see that, you could just sort of say the following. Suppose that we picked a v in the domain and its result, so let's just let omega 1 be t v. And let's also say that t of u is equal to 0 with u not equal to the 0 vector. So we have a non-trivial null space in this little example. Then we can build up all sorts of vectors if we want in the domain. For example, we could build up a z, which might be u plus v. And now if we operate on z with that linear map, that's now t of u plus v, but that's t of u plus t of v. T of u was 0. T of v, that's a pretty sloppy v, isn't it? That we assumed was w1. And now what do we have? We now have two vectors that live at the same location in the codomain omega sub 1, or w1. We have t of z equaling w1, which is equal to t of v. And that does not imply that z was equal to v, because z was actually v plus u, where u was some non-zero vector in the null space of t. And this now says that this is not a one-to-one map. I mean, we can go from z and go to w1. V will take us to w1. We could find another z3 and go to w1 if we wanted to. We could find all sorts of vectors that would map us to w1 if we have a non-trivial null space. And that's sort of the conclusion. If we have you have a non-trivial null space, then this linear map is not injective. And that's this connection then between an injective map and the null space. If you have an injective map, then you have a trivial null space associated with that linear map T. And that's what you can start thinking about in terms of this connection. Let's now look at sort of the counter concept to the null space, which is the range space. The range of a linear map is the set of vectors in the codomain W, which have, well, let me say which are of the form W equal TV for V in the domain. I don't know if these pictures are helpful or not, but here's a picture of this concept of range. We're going again from a vector space W into another vector space W with a map, a linear map T. But now we are interested in where do we get to in V. And it may not, I'm sorry, in W. And it may not be all of W. That's what this extra little blob is inside W. That's our range space of T. But that's the only place that points in V are going to map to. So there's our mapping T. And it really is then this range of T is now this script R, or range of T, and that's equal to the set of W equal TV such that V is anywhere in the domain. Stated another way, the range is everywhere you can get to in the codomain through this linear map T. In other words, the range of T is all the possible outputs in our codomain W. And one of the nice things is we knew that the null space of T was a subspace, but where was it a subspace in or of? So while the null space of T I'm guessing you said V. It was in the it was a subspace in your domain vector space. The range of T, so this was the null space of T. That's actually a subspace in the codomain. So the range of T is a subspace of W. So we showed that the null space was a subspace. Now you know how to show things are a subspace. It has to have three properties. And you can look in Axler for the proof that the range space is a subspace of the codomain. Let's now look at this second concept that we'd mentioned at the start of class, surjective, and show how it's related to the range space. So now here is this new term, surjective. Again, we take this linear map T, from V to W. that map is surjective if the range of T covers the entire codomain, or the range of T is equal to the entire codomain W. Stated another way, every vector in W so every possible location in the codomain, every vector in W is a possible output of T. If we wanted another sort of graphical picture of this, where this is our domain, the horizontal axis. Let's say our codomain is the vertical axis. Then we could have, I wanted that to be in blue, but so I better erase it. I'll never be able to. That's now a picture, if this is now f of x, of a surjective mapping. So this is not injective, but we are able to realize any number on the real axis with this function. If you give me minus 16, I can go over here to the location on the vertical axis at minus 16, and oh yes, the function does equal minus 16. So I'm able to span the entire, or cover the entire real line with this mapping. It may not be injective. It isn't, is it? Because now if I drew a horizontal line, I have not a one-to-one mapping. I could find maybe minus 3 equaling the same thing as minus 1 equaling the same thing as 5 in terms of values of x. But this is now a picture of a surjective map. And the thing that the book offers an example of is that it's important what your two spaces are, your vector spaces are, as far as what you're mapping from and what you're mapping into. For example, let's just say that it's crucial this mapping being surjective is crucially dependent on how the mapping T is defined. Suppose that I said, well, let's look at the differentiation mapping, but now let's say that we want that map to be operating between two vector spaces. Let's say, that's not how I drew it before. It's gonna be hard on my memory. P sub m, polynomials of order m, that's our domain, and let's say that our range is the same. Polynomials of order m. And let's say that T is our differentiation map. So if I give you a polynomial of mth order, that's P of x, and now I take the derivative of that with respect to x, that result does end up in this m-dimensional polynomial vector space, but does it cover the entire set of polynomials in that m-dimensional vector space? If I fix m, if I say, let's work with polynomials of order 3. So now I give you an arbitrary polynomial, or can you find an example of a vector in that third order polynomial set, which when differentiated once or mapped through here is not able to cover the entire vector space of third order polynomials? Or do you see what's going on here? Is this map surjective or not surjective? I need the derivatives to end up being any possible polynomial in this third order set of polynomials. Is that possible after I've differentiated once? What if I start with a third order? What happens when we differentiate a third order? X cubed. We lose an order, don't we? So every time we differentiate, we can't come back to a third order polynomial. So we're not going to cover that entire space. Is that clear? So this is a more abstract vector space relationship maybe, but now we are showing, hopefully, that this differentiation map for a fixed order M, that map is not surjective. Maybe it's cleaner if I say not surjective for a fixed M. And then I'll erase this thought. Here I'm using P sub M of R are nth order polynomials. If I change that around though, if I now say, suppose that I'm looking at all these linear maps, T, from P of M of R to P of M minus 1 of R, where T again is this differentiation map. Is that surjective? Can we get to any point in this M minus first order polynomial from mth order polynomials by differentiating once? Hopefully it's clear that it is surjective now. So this is surjective, that map for fixed M. Pictorially, what do we have? Now the range space, remember, was like this. That blue was maybe a subspace within W. For a map to be surjective, you need this blue to expand out and cover the entire W. That's a surjective map. It has to be now onto. You're covering everything onto W. That's what we mean by a surjective map. So a picture, which I'm not really going to probably show as cleanly, is if we start now with this domain V, and we end with W, and we're mapping through T, now, well, we may not even be coming from, it may not take all of V, but we're saying that everything covers the entire codomain, or the range of T is equal to the codomain, W, is what we're meaning. What's an example, maybe, of a non-surjective map? Maybe to just get us thinking about a mapping other than that particular picture. Well, what if I gave you the following? If this is now x, and this is now f of x, is that mapping surjective or not? If W, so now our mapping is the set x squared such that x is an element of R. Is this going to cover all of the real line? No. So this is not a surjective map. Is it injective? It's neither one, is it? So this picture is not injective and not surjective. Let's look at another example. Suppose that we say, well, let's look at a map T from R3 up to R5. And suppose now that we take this 3 vector, x, y, z, and we map it into a 5 vector, minus x plus y minus 3z, minus x plus 2y minus 4z, x plus y plus z, 2x plus 3y plus z, x plus 2z. Now, to be surjective, what would we need to have happen? We would need to be able to cover that entire 5-dimensional space with a vector from our domain. And in this case, I hope it's sort of clear that that's not going to happen. We only really have 3 coordinates, x, y, and z, and we're trying to expand that up to cover a 5-dimensional coordinate frame for a generic choice of 5 coordinates. What would this, if we now are looking at W, which is now T of V, V is x, y, z, if we look at what that needs to be relative to this 5-dimensional space, then if you just pull out the columns that are associated with scaling by x, the columns that are scaled by y, or the coordinates, how are they scaled by y, and the coordinates, how are they scaled by z, we have these 3 basically directions that we can adjust within this 5-dimensional space. We have the span then, W, the range of this linear map is going to be associated with the span of one vector is -1, -1, 1, 2, and 1. Do you see where that's coming from? Look at the coefficients associated with x. That's one combination of values. Now that's one vector, 5-dimensional vector. What about the coefficients associated with y? You have 1, 2, 1, 3, and 0. And then for z, we have -3, -4, 1, 1, and 2. Does everybody see where those vectors are coming from? So for arbitrary x, y, and z, we could then say x times this plus y times this plus z times this is where we can get to in our codomain space in W. For any combination of x, y, and z, the only places we can get to would be the span of these three vectors. And what do we know about spanning sets or the span of vectors? What's the dimension? What's the possible largest dimension that I could span with these three vectors? 3. I can only get into a 3-dimensional space with 3 vectors, even though they're 5 tall. They're 5 by 1, but I can only get to 3 directions in those with those vectors. But in fact, in this particular problem, the range of t, so this is now the range of t. That kind of, maybe I should have said this is now the range of t. I'm getting a little bit sloppy with my notation here. Range of t actually ends up being not those 3 vectors, but just there's some dependency among those 3 if you look at it. And in fact, you can show that the span of those 3 is covered by 2 vectors. So now that we're awake, we could see that 1, 0, -3, -7, -2, that vector span, and 0, 1, 2, 5, and 1 are the only directions that we can span. And now we have 2 vectors, which says then that in this particular example, the dimension of our range space is 2, which is less than the dimension of W, which was the dimension of R5, which was 5, which says that the range of T does not span all of R5, which allows us to conclude that T in this particular case is not a surjective map. And that particular relationship, we found vectors in the null space of that, which were beginning in the V, which were 3-dimensional. Now we have this range space that's in a 5-dimensional space, but it's only, the range space is only of dimension 2. So there's actually something going on here, and that's what I would like to sort of conclude with for today, and we'll have to pick up there. But let's look at theorem 3.4, and that relates these different dimensions. So if we're given our domain vector space, V, a finite dimensional vector space, I'm getting pretty quick with my wording, and T is a linear map, between V and W, then the dimension of our domain vector space is actually equal to the dimension of the null space of T plus the dimension of the range space of T. And we'll have to pick up at that point on Wednesday, but now we can think about these sizes or dimensions of these two spaces that we've now looked at, and we can actually show that their dimensions are equal to the dimension of our domain vector space. And that's where we'll pick up on Wednesday.